Over the past decades, imaging sensors have evolved at a rapid pace. The event camera is a bio-inspired technology that mimics the human eye and addresses the limitations of conventional imaging sensors. Characterized by its low latency, high dynamic range, and low computational requirements, event cameras open doors for new paradigms of robot perception algorithms. This visualization compares the output of such device compared to a standard camera with both sensors observe a black dot on a rotating disc. Unlike standard cameras, event cameras are triggered by the relative motion in the observed scene, firing a sparse, continuous event stream. By increasing the rotating disc speed, images from standard cameras suffer from motion blur, whereas the spiral of event camera is still clearly visible. Such unprecedented capabilities unveiled the power of event-based vision in space exploration, autonomous driving, and robotic manufacturing. In all of the aforementioned applications, intrinsic calibration is essential to account for lens distortions, and for robust pose estimation of the sensor. Therefore, our work proposes an event-driven calibration framework to robustly obtain the intrinsics of event cameras. To attain this aim, the proposed method comprises of the following contributions. First, an efficient reweighted least squares method is proposed to extract the feature points of the calibration targets. Second, a modified hierarchical clustering algorithm is devised to detect the calibration grid, apart from the presence of outliers and background clutter. And finally, we have validated our method in a variety of rigorous experiments for different sensor models, using different calibration patterns, and under challenging illumination conditions. Our approach involves utilizing an asymmetric circles grid, and an event camera observing the calibration pattern from multiple perspective views. The raw event stream is received from the sensor, and is fed into a spatiotemporal density-based clustering algorithm. This is essential in order to match the events to their corresponding calibration targets. The clustered events are fed into the efficient reweighted least squares optimizer, and are clustered to segment the feature points from the background clutter. Given the detected feature points, and the predefined pattern properties, calibration is performed, and the event camera intrinsic parameters are obtained. We validate our approach in the following experiment, of a fast-moving Davis 346 observing a 3x9 asymmetric circles grid. Notice that the Davis frames, E2-vid, and FireNet, suffer from degraded features when fast motion is induced, while the manifold regularization witnesses artifacts degrading the feature extraction performance. Our method, on the other hand, leverages the sparse nature of events, and the calibration targets are robustly captured even during aggressive maneuvers with a low reprojection error. We benchmark our approach against state-of-the-art methods for calibrating event cameras, which include the manifold regularization, E2-vid network, FireNet network, and Event-Calib. All the approaches were compared on the publicly available E-Cam asymmetric circles dataset, and the quantitative metrics are the reprojection error, positioning error, detection success rate, and the computational time. Notice that our calibration framework provides a high detection success rate and a low reprojection error, even at challenging illumination conditions. Similarly, for positioning error, our method provides a positioning accuracy with sub-centimeter precision even in poorly lighted environments. We also cross-validated our method against the state-of-the-art, and outperforms them in terms of reprojection error, positioning error, and detection success rate. In addition, our algorithm computational time shows the capability of performing online calibration of event cameras. Thank you for watching.